Okay, so let's now continue, and we'll now simulate the first collision. So we take the expression for the parametric vector equation, and we set in the values of t of the parameters, and then we get our equation for t, which looks like this. So it's got a tiny little term which should ideally be 0, but because of round offs. And so you can see that the solutions of this are either t equals 0 or t equals this divided by this. So let's do that. So we take the coefficient of t in this expression and divide it by the coefficient of t squared. And that should assign the value of t at the next collision. And there it is. And now we use that to find the position of the next collision. It gives us that. And then we can append that to the file of collisions using that. So now we've had 2 collisions, and these are the points where or the coordinates of the points where they occurred. And now we take the initial velocity and we subtract off twice the component of the velocity in the radial direction, and that gives us that. And now we now update the initial position to be where that one occurred, and we update the velocity to be that. And now we can keep doing that as long as we like. And this, by the way, is the way we develop small programs. So we've actually developed an iterative cycle here. So all we do is we put all those instructions together in this little bit of code here, and then we repeat it 200 times. So all I've done is pasted those instructions in here, and we now do 200 of those. And that didn't take long. And now let's look at the trajectories. So what I'm going to do is I'm going to plot the coordinates of those points in 3 dimensions and show that they all lie on a circle. So here it is. And there you can see, oops. There's the, so that's kind of convincing, I hope. Or we can look at the square of the lengths of the points, and we can see they're all 1, so indeed they lie on the circle. And then we can take the scalar product between the a position and the next position, and it looks like this. And for some reason something happens with the first one, but after that they're all the same.
What happens to the first one?
I don't know. I've got to look into that.
Mm-hmm.
But it doesn't affect the argument. And now, to show that they all lie on a plane, we do what we did before. We take the scalar product of any one with the vector product of the next 2. Sorry, the vector product of the previous one and the next one.
Yeah.
And you can see that they're all very small numbers. So in other words, that verifies that they're all on a plane. So all well and good. Let's carry on and complete the argument. So every time a particle strikes the wall of the container, its radial component of velocity is reversed, and that must imply that by the principle of conservation of momentum, that an amount of momentum equal to the radial component of the velocity, or twice the radial component of the velocity, is transferred to the container.
And perhaps I should say here that the reason we want to have the momentum changes is that this will eventually give us an expression for the energy.
Yeah. Right. So from Newton's laws of motion, if we divide the change in momentum by the time, then that's the rate of change of momentum, and that should be the force which the particle exerts on the container. So we do that. We better do the momentum first. And we do the force. If we now look at the force, isn't that beautiful? So the force is just proportional to the kinetic energy. If we now divide the force by the area, then that should give us the pressure. So we do that. And the volume of the container, of course, is given by that. So we can multiply the pressure by the volume and see what we get. Well, that is exactly 2/3 of the kinetic energy. And since the particles never collide with each other, we can sum this expression over all the particles. So the product of the pressure exerted by the gas on the walls of the container and its volume can be seen to be 2/3 of the kinetic energy of all the particles.
Yes.
Anyway, it's left as an exercise to reproduce this result using abstract vector analysis rather than spherical coordinates. You'll have a lot of fun with that. Okay, so now our conclusion is that the kinetic energy of an ideal gas is equal to 3/2 times the pressure times the volume, where P is the pressure and V is the volume of the container. Now, since the particles in an ideal gas do not interact, the only energy they can have is kinetic. So we interpret this as the internal energy function of the ideal gas, go away, Bill, which can be established using this. So this is a mathematical function which has formal arguments, and we'll see the reason for doing that. Well, the reason for doing it is we can apply this function to any particular value. So here it is here, and there it is there.
And we see that it is an expression that involves only known parameters like the pressure and the volume.
Yeah. Now, elementary treatments, or traditional treatments, I'd say, now confuse an ideal, in brackets, or Knudsen gas with a real gas, where the atoms have finite size and so continually collide with each other, exchanging energy in the process, so that their speeds change. And under certain assumptions, the probability density of the speed of atoms can be shown to converge to a stable distribution, the Maxwell-Boltzmann distribution, which depends on the as yet undefined temperature of the gas. From this distribution, and assuming that temperature has been defined, it can be shown that the kinetic energy of the gas is proportional to this temperature. However, we don't want to go there. As the purpose of the whole exercise is to arrive at the definition of temperature, we believe that this assumption is a tautology which can only confuse students. In subsequent sections, we show that this is unnecessary and that the observation that the internal energy function is given by this is sufficient to carry out the analysis of the Carnot cycle and show that the temperature of an ideal gas is proportional to this function.
Good.